Now today's part is conservation of angular momentum. In 11th standard we have studied conservation of linear momentum. When there is no force acting on colliding bodies, then total momentum before collision is equal to total momentum after collision. How? See this example. Linear momentum is given by formula P equal to m into v. Linear momentum is a product of mass and velocities. In this figure you can see two bodies. Mass of first body is 10 kg, mass of second body is 4 kg. First body is moving with velocity 8 meter per second. Second body is moving with velocity 5 meter per second. Therefore momentum of first body is 10 into 8, mass into velocity 80, while momentum of second body is 4 into 5, mass into velocity, that is 20. Their total momentum is 80 plus 20 equal to 100. Now as this body is moving with velocity greater than velocity of second body, after some time this body of 10 kg will collide on this second body of 4 kg, and after collision the bodies will get separated from one another. Their masses will remain same. Mass of first ball was a 10 kg before collision, and after collision also mass of first body is 10 kg and that of second body is 4 kg before and after collision. But velocity changes. Initially the velocity of first body was 8 meter per second before collision. Now velocity of first body is 4 meter per second, that is after collision. Velocity decreased. In the velocity of second body was 5 meter per second. Now that velocity is 15 meter per second. But see their momentum. Momentum of first body is 10 into 40, mass into velocity. Mass 10 into velocity 4, that is 40. For second body, mass 4 into 15, that is equal to 60. Total momentum is 40 plus 60 equal to 100. Therefore total momentum of two bodies together before collision was 100, and total momentum after collision is again 100. That means momentum is constant. This is called as law of conservation of linear momentum, and that we have studied in 11th standard. But there is a one condition. There should not be external force acting on these colliding bodies. These bodies can exert force on one another. By Newton's third law, there can be action-reaction forces during collision, but there should not be external force acting on these colliding bodies. Only just like law of conservation of linear momentum, there is a law of conservation of angular momentum in rotational motion. Angular momentum is given by formula L equal to I into omega. I means moment of inertia and omega is angular velocity. This law is obeyed when there is no torque acting on rotating body. If torque acting on rotating body is 0, then this angular momentum will remain constant. If moment of inertia increases, angular velocity will decrease, but their product will remain constant. See this example. I1 omega 1 means suppose this person rotates about its own axis passing through his body, and when he outstretches his arms, then moment of inertia increases, moment of inertia is more. In that case angular velocity will be less. Say initially suppose the moment of inertia of that person is 25, angular velocity is 4. Now when the person folds his arms, then moment of inertia decreases, becomes 20. From 25 moment of inertia becomes 20, but angular velocity increases from 4 to 5. But product remains same. See, initially the product was 25 into 400. In second case also the product is 25 into 5 equal to 100. So angular momentum is constant when moment of inertia decreases. See in this example, moment of inertia decreases from 25 to 20, and angular velocity increases from 4 to 5, but their product angular momentum remains constant. This is law of conservation of angular momentum, provided there is no external torque acting on the body. Now angular momentum, now moment of inertia increases when the mass distribution increases. When this person spins about an axis passing through the body itself, and when the person outstretches the arms, then mass distribution increases and moment of inertia decreases. When moment of inertia increases, angular velocity decreases. See in that video. When he outstretches the arms, speed decreases. When he folds the arm, speed increases. This is law of conservation of angular momentum. Now we have to prove this law of conservation of angular momentum. To prove the law of conservation of angular momentum in vector form is given by vector r cross vector p. This we have already seen in one earlier part. Now to prove this law of conservation of angular momentum, take derivative of both sides. Differentiate above equation with respect to time. That means take derivative with respect to time. dl upon dt equal to d by dt of vector r cross vector p. Now suppose keeping p constant, take derivative of r first, and then keep r constant and take derivative of p. After that, we know this dr upon dt, rate of change of this position vector, is nothing but velocity, and rate of change of momentum is force. dp upon dt equal to f. Keep these values in this equation. And also we know that momentum is mass into velocity. Therefore, keep these three values in this equation. dr upon dt, replace that dr upon dt by v, replace this dp upon dt by f, and this p by mv. We get next step. From that, we can write this equation in this way. The same equation, m is taken first, then v cross v plus vector r cross vector f. Now we know cross product or vector product of a vector with itself is equal to 0. Therefore, this v cross v will be 0. And also we know that cross product of position vector and vector f is torque. This is expression for torque. Therefore, v cross v is 0 because vector product of a vector with itself is always equal to 0. This we have learned in 11th standard. And vector r cross vector f in vector form, that is actually rf sin theta. This is equal to torque. Keep these values in above equation. We get this equation. From that we get this equation. By changing the sides, we can write this equation. Now when torque is 0, then dl upon dt will be 0. When dl upon dt is 0, means L is constant, because the derivative of any function will be 0 only when that function is constant. When torque is 0, means dl upon dt is 0, means derivative of this L is 0. And we know derivative is 0 only when that function is constant. Derivative of constant function is 0. Therefore, if L is constant, means its derivative is 0, torque is 0. Therefore, torque to be 0, torque will be 0 only when this L is constant, and this is proof of law of conservation of angular momentum. When torque is 0, angular momentum remains constant. Now we will see some examples of conservation of angular momentum. When person spinning about his own axis stresses arms, then moment of inertia increases and angular velocity decreases.
I'm not a very good skater, so I'll use this turntable and a pair of hammers. I'll hold them out at arm's length so I get a nice large radius, and I'll set myself in a slow spin. I'm spinning around at a constant speed, and then I draw the hammers close to my body, and I spin around very rapidly. As soon as I move them out, I slow down again. And I can repeat this as many times as I want until the friction of the turntable stops me.
This is one more example of law of conservation of angular momentum. When ballet dancer spinning about herself, folds her arms, moment of inertia decreases and therefore angular speed increases. On the other hand, when she outstretches her arms, moment of inertia increases and therefore angular speed decreases. See this video. Another example of conservation of angular momentum. On the diving board, the divers stretch their body so as to increase the moment of inertia. Immediately after leaving the board, they fold their body. This reduces the moment of inertia considerably. As a result, the frequency and angular velocity increases and they can complete more rounds in air to make the show attractive. Again, while entering into water, they stretch their body into a streamline shape. This allows them a smooth entry into the water.